Galaxies are locked in a slow-motion dance of unimaginable scale. This is not a story of destruction, but one of cosmic creation. When galaxies collide, they engage in a gravitational ballet that forges new stars and entire worlds from the chaos. By the end of this journey, you will understand how our own galaxy's future is written in these celestial mergers. We will uncover what happens when supermassive black holes tango at the heart of a collision, and how a violent cosmic event could be the very cradle for new life. What does it mean for our home to be part of such a dynamic and evolving universe? The vast emptiness of space is an illusion, a cosmic stage set for perpetual motion. Galaxies are not frozen sculptures but living, breathing entities, each one a gravitationally bound metropolis of billions of stars. This stellar city is held together by an unseen force, the mysterious grip of dark matter, a ghostly halo that dictates its every move. Within these cities, the real magic happens in the dark clouds between the stars. Immense reservoirs of gas and dust drift through the spiral arms, a frigid interstellar fog that serves as the nursery for everything to come. It is from this primordial stuff that new suns ignite and new worlds coalesce. Our own Milky Way is a classic spiral, a pinwheel of light and shadow, but look further and you find a zoo of galactic shapes. Some are smooth, featureless ellipses, vast swarms of ancient stars. Others are chaotic and irregular, their forms twisted by past encounters. This incredible diversity reveals that a galaxy's appearance is a snapshot of its life story, a story often rewritten by its neighbors. Because these islands are never truly alone, their immense gravitational fields reach out across the void, whispering to one another. This inherent connection means a close pass is not a freak accident, but an inevitable chapter in a galaxy's evolution. The dance begins with this faint, persistent pull, a cosmic invitation that can last for billions of years. The seeming contradiction of an expanding universe and colliding galaxies resolves itself when we look closer at the cosmic map. While space itself is stretching, pulling vast clusters of galaxies apart from one another, gravity reigns supreme on more local scales. Think of it like a bustling city. The entire metropolitan area might be growing, pushing the outer suburbs further away, but downtown, the buildings are tightly packed, their proximity dictating a constant dance of interaction. On the grandest stage, galaxies are not spread evenly like raisins in a rising loaf of bread. Instead, they gather into immense clusters and superclusters, vast archipelagos bound by their mutual gravitational pull. These are the true cities of the cosmos. Our own Milky Way is part of such a community, a small gathering known as the local group. Here, we are not flying apart. We are all orbiting a common center of gravity, a slow, stately waltz that has been ongoing for billions of years. And in this dance, close encounters are not a matter of chance, but a matter of time. The most famous example is our own galactic future. The Andromeda galaxy, a faint smudge of light in our night sky, is not a distant, static neighbor. It is a partner in this cosmic ballet currently hurtling towards us. We are on a direct collision course, a merger that has, in a gravitational sense, already begun. This inevitability transforms our perspective entirely. Galactic collisions are not freak accidents or violent disasters. They are a natural, recurring phase in the life of a galaxy, a fundamental process of renewal that has been shaping the universe since its earliest days. This slow-motion merger begins with a gentle, irresistible pull. Even from millions of light-years apart, the gravity of one galaxy reaches out and begins to tug on the other. They are drawn together in a long, graceful arc, a celestial courtship that unfolds over hundreds of millions of years. At first, they might simply glide past one another, a near miss on a cosmic scale. But a close pass is all it takes to unleash chaos. Long before any stars actually crash into one another, a more subtle force goes to work. This is the effect of tidal forces. Imagine the difference in gravity between the side of a galaxy facing its partner and the side facing away. That difference creates an immense stretching pull. It is this gravitational tug of war that begins to tear the galaxies apart. The serene spiral arms, once perfectly defined, become warped and twisted. They lose their elegant shape, becoming grotesque and distorted. From these galaxies, immense rivers of gas, dust, and stars are pulled out into the void. These are the tidal tails, luminous streams that can stretch for hundreds of thousands of light years, acting as ghostly banners heralding the collision. This is the galactic tango, a slow and devastatingly beautiful prelude where both partners begin to lose their original forms, setting the stage for a far more violent and intimate embrace. This gravitational courtship soon escalates into a full embrace. The galaxies are no longer distant partners influencing each other from afar, their gravitational fields now deeply intertwined. They lock into a complex orbital dance, often swinging past one another not just once, but multiple times. With each close pass, a gravitational transaction occurs, energy and angular momentum are traded, and their orbits slowly decay, pulling them ever closer together in a tightening spiral. During this intimate merger, the very hearts of the galaxies are drawn into the fray. The galactic cores, each likely harboring a supermassive black hole of unimaginable mass, begin their own separate waltz. They sink towards the center of the new, combined system, two titans circling one another in the dark. This cosmic turmoil throws the orderly rotation of billions of stars into utter chaos. Stars that once followed predictable, circular paths are now flung onto wild, erratic orbits, creating a celestial mess. Yet, from this chaos comes an incredible burst of creation. The vast clouds of interstellar gas, once drifting peacefully, are now violently compressed and shocked by the gravitational forces. This triggers a frenzy of new star birth, a stellar baby boom of epic proportions. Entire clusters of brilliant, hot, young stars ignite in a blaze of glory, lighting up the merging galaxies from within. This stage is a cosmic paradox of both creation and destruction, where the old, familiar structures are completely dismantled to make way for something entirely new. It is a fundamental and violent alteration of fate for every star, every planet, and every cloud of dust caught in its grasp. Yet the stars and glowing gas clouds are merely the performers in this ballet, not its choreographers. The true director of this cosmic dance remains utterly invisible to our telescopes. We are only seeing the luminous tip of the galactic iceberg. The vast majority of a galaxy's mass, the very anchor of its immense gravitational field, is made of something we cannot see, dark matter. This mysterious substance does not emit, absorb, or reflect any light, making it completely transparent. It reveals its presence only through its relentless gravitational grip. Each galaxy is embedded within an enormous, diffuse sphere of this dark matter, a halo that extends far beyond its visible edge. This halo is the true skeleton of the galaxy, the framework that dictates its every move. When two galaxies collide, we witness a spectacularly misleading event. The bright, familiar components of stars and gas clouds slam into each other, but their dark matter halos do something entirely different. They simply pass right through one another, because dark matter particles are thought to interact only through gravity and not the electromagnetic forces that make normal matter solid. They feel no friction. They do not crash, they do not heat up, they ghost through their partner as if it were not even there, yet their gravitational influence is profound. It is these interpenetrating dark matter halos that steer the entire merger. Their immense, unseen mass creates the gravitational wells that the visible galaxies fall into, orchestrating the complex orbital dance from behind a cosmic curtain. This is why understanding dark matter is not just an academic puzzle. It is the key to explaining why galaxies move the way they do within vast clusters, and how the very largest structures in our universe were first built. Dark matter provides the unseen framework for the entire cosmic ballet, a hidden architecture that guides the birth and evolution of everything we can see. This violent compression of gas and dust is where chaos becomes a cradle. As the two galaxies intertwine, their vast interstellar clouds do not simply drift past one another. They are forced together in a colossal, cosmic traffic jam. The result is a celestial fireworks show known as a starburst. Imagine the quiet, steady star formation of a normal galaxy like our Milky Way, a process of gentle, ongoing construction. Now contrast that with the furious, explosive construction boom of a galactic merger. Here, the rate of star birth can skyrocket, creating new suns at a pace hundreds or even thousands of times faster than before. The galaxy essentially gives birth to an entire generation of stars all at once. These are not just any stars either. The conditions favor the formation of many truly massive, brilliant, blue-white suns. These stellar giants burn with a ferocious intensity, flooding their surroundings with ultraviolet light and powerful stellar winds. They are the rock stars of the cosmos, living fast and dying young in spectacular supernova explosions. The entire region glows with an almost unbearable brilliance, a beacon of creation visible across the universe, but much of this light is initially hidden. The same dense clouds of dust that spawned these new stars also absorb their fierce radiation, heating up until they themselves glow, not in visible light but in the infrared. This is why many of the brightest objects in the infrared sky are not single stars, but these colliding galaxies, their starburst hearts shining through the cosmic dust that shrouds them. This frantic burst of creation, however, is more than just a spectacle. It is a fundamental act of cosmic recycling. Those massive stars, in their short lives and violent deaths, forge heavy elements in their cores, everything from the carbon in our bodies to the oxygen we breathe. When they explode, they seed the surrounding gas with these newly forged elements, enriching the galaxy for the next generation. The iron in your blood, the silicon in the ground beneath your feet, all were likely born in such a stellar furnace during a long-ago collision that turned chaos into the very building blocks of worlds. A single star passes through this cosmic upheaval almost entirely untouched. The most persistent myth about colliding galaxies is a sky filled with stellar fireballs, suns crashing into one another in a series of apocalyptic explosions. The truth is far stranger and speaks to the profound emptiness of space. Within a galaxy, stars are not packed together like a bustling crowd. They are more like a handful of fine sand scattered across an entire continent. The distances between them are so incomprehensibly vast that a direct collision is one of the rarest events in the universe. The real action is not in physical impacts, but in the invisible push and pull of gravity. As the galaxies merge, their combined gravitational field becomes a chaotic storm. Imagine a star once following a calm, circular orbit, suddenly caught in this turmoil. It can be slingshotted by a gravitational encounter, sent flying onto a wild new path. Some stars receive such a powerful kick that they are ejected entirely. thrown out of the galaxy at incredible speeds to become lonely travelers in the blackness of intergalactic space. These are the hypervelocity stars, cosmic exiles cast out from their homes. Others have the opposite experience, their orbits decaying, pulling them inexorably inward toward the frenetic activity of the galactic core. The entire stellar population is thrown into a giant mixer, with stars from the two original galaxies becoming thoroughly intertwined. Yet through it all, the average star, with its possible system of planets, remains physically unharmed. Its journey is simply redirected, its fate rewritten by the grandest gravitational reshuffling imaginable. So what becomes of these cosmic whirlpools after their great merger is complete? The final product of this slow-motion collision is often one of the universe's most serene and ancient-looking structures, an elliptical galaxy. These vast, smooth, and featureless islands of stars represent a fundamental endpoint in galactic evolution. Their majestic, rounded forms are a direct result of the violent relaxation and orbital scrambling we just witnessed. When two spiral galaxies of roughly equal size finally merge, the gravitational chaos fundamentally rewrites the rules for every star within them. The delicate, orderly rotation of a spiral disk, where stars orbit in a single, flat plane like horses on a carousel, is completely erased. In its place, you get a system where stars fly about in every conceivable direction, a three-dimensional swarm with no central plane or clear axis of rotation. This creates a stable but far more chaotic configuration, a celestial beehive where the collective motion of the stars averages out into that smooth, ellipsoidal glow. This transformation also marks a dramatic shift in the galaxy's life cycle. Many of these newly forged elliptical galaxies are what astronomers call red and dead. They are dominated by the reddish glow of older, cooler stars. The reason is starkly simple. The ferocious burst of star formation that lit up the merger used up nearly all the available fuel. The great clouds of gas and dust, the raw material for new suns, were either consumed in that final starburst or blown entirely out of the galaxy by the powerful winds from all those massive stars and supernova. Without this cold, dense gas, the galaxy can no longer form new stars. Its stellar population simply grows older together, fading slowly over billions of years. This is a profound change of identity. A spiral galaxy, with its ongoing star birth and dynamic structure, is a living, evolving system. An elliptical galaxy born from a merger is often a quiet retirement home for stars, a fossilized remnant of a single, violent, and transformative event. This pathway from a star-forming spiral to a quiescent elliptical shows that collisions do not just reshape galaxies. They can create entirely new classes of galactic objects, fundamentally altering the family tree of the cosmos. But the most spectacular cosmic debris can sometimes become something new entirely. Those long, flowing rivers of stars and gas we call tidal tails are not merely temporary features. If a tail contains enough material, a remarkable transformation can occur. The immense gravitational pull within the stream itself can cause it to fragment and collapse, knotting up to form entirely new, independent galaxies. These are the tidal dwarf galaxies, cosmic orphans born from the wreckage of a collision. They are fundamentally different from their colossal parents. Because they are forged from material ripped out of the galactic disks, they are made almost entirely of the normal matter we can see and touch, the gas and stars astronomers call baryonic matter. The ghostly dark matter halo, the true gravitational anchor of the original galaxies, was left behind in the central merger. This makes tidal dwarf galaxies incredibly valuable to science. They are natural experiments, cosmic islands where we can study how stars and gas behave without the dominant influence of dark matter. Observing them helps us untangle the separate roles of these two components, clarifying how invisible dark matter shapes the grand architecture of the universe, while normal matter builds the luminous structures within it. At the very core of this cosmic restructuring, a more intimate and powerful dance begins. Nestled within the heart of each original galaxy is its ultimate secret, a supermassive black hole weighing millions or even billions of times more than our Sun. As the galaxies spiral together, these gravitational monsters are dragged by friction and dynamical forces toward the center of the newly forming system. There they find one another. Initially, they are often separated by thousands of light years, but their mutual pull is irresistible. They begin to orbit one another, forming a binary pair, two titans locked in a gravitational embrace. This is not a stable partnership. As they circle, they interact with the dense environment they helped create, flinging stars away on new trajectories and plowing through any remaining gas. Each gravitational interaction acts like a tiny brake, stealing a minuscule amount of energy and angular momentum from the pair. Over millions of years, this slow, steady loss of energy causes their orbits to decay, drawing them ever closer in a tightening spiral. This inward journey can unleash a spectacular display. If significant gas remains in the galactic core, it is drawn into a frantic, hot whirlpool around the black holes, an accretion disk glowing with intense friction. This process can ignite an active galactic nucleus, a beacon of light so brilliant it can outshine every single star in the merged galaxy combined. The final act of this billion-year dance is one of unimaginable violence. When the black holes spiral close enough, they merge in a single, cataclysmic event. This collision is so powerful that it does not just release light, it shakes the very fabric of the cosmos, sending ripples through space-time known as gravitational waves. This is the crescendo of the entire galactic merger, a silent, universe-spanning shout that confirms the birth of a single, even more massive black hole, the new dark heart of a transformed galaxy. That final, silent crash between two supermassive black holes sends a tremor across the cosmos. This is not a tremor of light or sound, but a vibration in the very stage upon which the universe is built, a ripple in space-time itself. These are gravitational waves, a phenomenon predicted by Albert Einstein over a century ago. His theory of general relativity revealed that space and time are not a static backdrop, but a flexible, dynamic fabric. Massive objects warp this fabric, and when they accelerate, they can create waves that travel outward at the speed of light. Think of the universe as a vast, still pond. Dropping a single pebble creates tiny ripples, but the merger of two supermassive black holes is like dropping two mountain-sized boulders into that pond. The resulting waves are immense, carrying away a staggering amount of energy directly from the orbit of the black holes. This loss of energy is what seals their fate, acting as a final, irresistible brake that pulls them into their last, fatal spiral and ultimate collision. We have already begun to listen to these cosmic tremors. Ground-based observatories have detected gravitational waves from the mergers of smaller, stellar mass black holes, events that are powerful but fleeting. The waves from supermassive black holes are different. They are a deeper, lower-frequency hum, a bass note in the cosmic symphony. These waves are so long that their peaks and troughs could take years, even decades, to pass by. To hear them, we cannot listen from Earth. Our planet's own background hum and the small size of our detectors make it impossible. The future of this exploration lies in space. Ambitious projects like the Laser Interferometer Space Antennae, or LISA, are being designed to float in the vacuum beyond our world. This formation of spacecraft will act as an enormous ear, listening for the low-frequency gravitational choir of supermassive black holes merging all across the universe. Catching these specific signals will be like hearing the final, resounding chord of the galactic dance, a direct confirmation of a process we have so far only been able to watch from a distance. It will open an entirely new sense with which to observe the cosmos, allowing us to perceive the universe not just by its light, but by its very vibrations. The silent passage of stars through a galactic collision hides the true drama unfolding in the spaces between them. This is the realm of the interstellar medium, a name for the thin, ghostly fog of gas and dust that drifts through a galaxy's spiral arms. While stars may glide past one another untouched, these immense clouds of hydrogen and microscopic dust grains have no such luck. They are the true protagonists of creation in this cosmic story. When two galaxies intertwine, their respective clouds of gas slam into one another at phenomenal speeds. These are not gentle mergers but violent, supersonic impacts. The collision sends powerful shock waves rippling through the clouds, acting like a cosmic snowplow. These waves push the gas ahead of them, compressing it into incredibly dense knots and filaments. Within these newly forged dark wombs, gravity finds its ultimate opportunity. The immense pressure overcomes the gas's natural tendency to expand, triggering a runaway gravitational collapse. A pocket of gas begins to contract, heating up as it falls inward until nuclear fusion ignites at its core and a new star is born. This is the primary engine of the starburst, turning a chaotic traffic jam of gas into a brilliant stellar nursery. But the role of this interstellar fog goes far beyond simply making new suns. The violent turmoil of the merger acts as a giant blender for the entire galaxy. It stirs together different populations of gas that might have remained separate for billions of years. Some clouds might be pristine, composed almost entirely of primordial hydrogen and helium from the dawn of time. Others are already enriched, laced with heavier elements like carbon, oxygen, and iron, elements that were forged in the hearts of earlier generations of massive stars and scattered by their supernova deaths. A collision mixes these different recipes together, creating a more uniform and, crucially, a more enriched blend of cosmic material. This is a vital step for the universe's creative potential. All the elements essential for rock, for water, and for life itself were made in stars. A galactic merger ensures these precious materials are not locked away in isolated pockets, but are churned and distributed throughout the new galaxy. This enriched gas and dust will eventually cool and coalesce into new generations of stars, but this time they will be born with the ingredients for planets already present. The swirling disks of material around these infant suns will be peppered with silicon, iron, and complex carbon molecules, the very seeds from which new worlds and perhaps even life can spring. Without this diffuse, gaseous component, the entire spectacle of a galactic merger would be a dim and quiet affair. The brilliant starbursts that light up the universe would never ignite. The heavy elements would remain locked away, and new planetary systems would be far scarcer. It is the collision and compression of this interstellar medium that transforms a slow-motion gravitational dance into a brilliant creative fire. This invisible fog is the raw clay of the cosmos, and a galactic collision is the immense hand that sculpts it into new suns, new worlds, and new possibilities. This cosmic dance is not a distant spectacle, but our own galaxy's destiny. The Milky Way and its great neighbor, the Andromeda galaxy, are already falling towards one another at a breathtaking speed of 110 kilometers every second. We are on an inevitable collision course, a merger that has, in a gravitational sense, already begun. The full, drawn-out embrace will start in about 4.5 billion years, a timescale so vast it dwarfs human history, yet it is a definitive chapter in our galaxy's story. Imagine watching this unfold from a future Earth. the familiar band of our Milky Way would slowly be joined by another, growing from a faint smudge into a brilliant, sprawling tapestry of light. The two great spiral structures would intertwine, their forms twisting and distorting until they are no longer recognizable, their stellar populations thrown into a cosmic blender. The final product of this billion-year process will likely be a single, massive elliptical galaxy, a smooth island of stars that astronomers have playfully nicknamed Andromeda. This is not science fiction. It is the forecast for our home based on precise measurements of Andromeda's motion. This future event transforms an abstract cosmic process into something deeply personal. It connects the grand, universal narrative of colliding galaxies directly to our own cosmic address, revealing that we are not mere observers of the universe's evolution, but active participants in its endless, beautiful turmoil. A mere 60 million light-years away, we have a front-row seat to the cosmic dance in full swing. The object known as the Antennae Galaxies offers a perfect snapshot of this violent and creative process. These two spiral galaxies, locked in a close embrace, are named for the two spectacular streams of stars arcing far into space, resembling the delicate antennae of some colossal insect. These are the tidal tails we discussed, but here we see them not as a theoretical concept, but as a breathtaking reality, luminous proof of the immense gravitational forces tearing these once orderly spirals apart. The galaxies themselves are a mess of beautiful chaos. Their classic pinwheel shapes are long gone, replaced by a tangled knot of dust lanes and brilliant blue-white clusters. These clusters are the stellar baby booms, the starbursts, happening right now. Each brilliant knot represents a firestorm of star formation, where thousands of new suns are igniting from the violently compressed gas. The cores of the two original galaxies are still visible as two distinct, bright regions, but they are drawing inexorably closer, caught in the final stages of their gravitational spiral. For astronomers, the Antennae system is more than just a pretty picture. It is a living laboratory. It shows us the intermediate stage of a merger, a phase that is too rapid to catch in most other systems. Here, we can directly study the physics of colliding gas clouds, measure the intense radiation from newborn star clusters, and watch as the heavy elements forged in supernova are scattered into the surrounding chaos. This single, chaotic system validates the entire story, providing a real-time view of the tidal forces, starbursts, and cosmic recycling that define the transformation of galaxies. Just as one cosmic dance reaches its climax, another begins with a graceful and intricate prelude. The mice galaxies present a stunningly different portrait of an encounter, one defined not by a final, fiery merger, but by an elegant, drawn-out courtship. Here, two spiral galaxies are caught in an act of extreme gravitational stretching, their long, slender tails streaming away from them for hundreds of thousands of light-years. These are not the chaotic plumes of a final collision, but the precise, beautiful arcs of a very close pass. Their name is wonderfully apt, as they look like a pair of celestial mice, forever fleeing from one another, connected by their luminous, flowing tails. This is the moment where tidal forces are at their most artistic, sculpting the galaxies into these extraordinary shapes long before their cores have any thought of merging. The specific geometry of this encounter is a gift to science, because we see the mice from a particular angle, and because they are in this early, clean stage of interaction, astronomers can use them to decode the exact physics of how these immense structures are torn apart. They can measure how much mass is being stripped away into the tails and track the complex transfer of energy and spin that is fundamentally altering the orbits of billions of stars. The mice teach us that no two galactic collisions are ever the same. Each encounter is a unique composition, its final form dictated by a precise recipe of mass, speed, and the all-important angle of approach. A direct head-on crash will create a very different kind of chaos than a slow, grazing pass. A collision with a small companion will have a different outcome than a merger of two titans of equal size. This variety shows that the cosmic dance is not a single, rigid choreography, but an infinite improvisation, with each pair of galaxies writing their own unique and fleeting story across the void. The same cosmic fire that forges new worlds also holds the power to sterilize them. Galactic collisions present a profound paradox for life, a double-edged sword of cosmic proportions. On one hand, the furious starbursts and the brilliant active galactic nuclei unleash a torrent of lethal radiation. X-rays and gamma rays flood the merging galaxies, creating an environment so hostile that it could strip away planetary atmospheres and scour the surfaces of any worlds orbiting too close to the action. For any life forms existing in those regions, this would be an apocalypse, a swift and unforgiving end. Yet, from this same cataclysm, the seeds for new life are sown. The violent deaths of massive stars in supernova explosions and the frantic activity around the merging black holes are the very furnaces that create and distribute the heavy elements essential for planets and biology. Carbon, nitrogen, oxygen, and iron are blasted into the interstellar medium, enriching the galactic gas. When this enriched material later cools and collapses to form new stars, those stars are born with a rich supply of planet-building material. This means that the second and third generations of stars formed after the merger are far more likely to have rocky, terrestrial planets and the complex chemistry needed for life to eventually emerge. This creates a delicate habitability window. Immediately following the collision, the galaxy is a death zone flooded with radiation. But as the most massive stars quickly burn out and the central black hole activity quiets, the radiation levels subside. The galaxy enters a new, more stable phase. Now, around countless new, stable stars, there are countless new planetary systems, each one forged from elements created in the collision itself. A galactic merger, therefore, acts as a cosmic reset button. It may end one chapter of habitability, but it dramatically sets the stage for the next, potentially giving rise to more life-bearing worlds than the original galaxies ever could have sustained on their own. These dense, metal-rich clouds are more than just stellar factories. They are the assembly lines for entire worlds. Within the furious starburst of a galactic merger, thousands of new suns ignite almost simultaneously, and around each one, a swirling disk of leftover gas and dust takes shape. This is the protoplanetary disk, a vast, flat whirlpool of material that becomes a cosmic construction site. Inside these disks, microscopic particles of dust, now heavily laden with elements like iron, silicon, and carbon, begin to stick together. They form pebbles, then rocks, then mountain-sized planetesimals, colliding and merging in a chaotic dance of accretion. The sheer abundance of heavy elements is the key. In a galaxy that has not experienced such a violent enrichment event, the disks around young stars might be sparse, containing mostly hydrogen and helium, the lightweight building blocks of gas giants. But here, in the aftermath of a collision, there is a wealth of solid, rocky material. This dramatically shifts the balance of what kinds of planets can form. The probability of creating dense, terrestrial worlds like Earth, Mars, and Venus skyrockets. These are not just barren rocks either. The same cosmic clouds are also rich in water ice and complex carbon molecules, the fundamental ingredients for oceans and potentially the chemistry of life. So, while the galactic collision rages on a macro scale, on a micro scale, within countless quiet eddies of these turbulent disks, the quiet, patient work of building new planets begins. A single merger can seed an entire galaxy with a new generation of solar systems, each one a potential cradle for whatever comes next. These ancient, glittering swarms of stars may hold the deepest memories of a galaxy's past. Globular clusters are dense, spherical collections of hundreds of thousands of stars, all bound together by gravity in a tight-knit community. They are among the oldest structures in the universe, often considered cosmic fossils that formed when the cosmos was young. But their story is not just one of ancient, isolated birth. These stellar relics are also deeply entwined with the violent history of galactic collisions. During a major merger within the frenzied starburst regions where gas is compressed to an extreme, something remarkable can happen. The conditions become so intense that they birth not just individual stars, but entire, massive globular clusters all at once. These newborn clusters are distinct from their ancient cousins. They glow with a brilliant blue-white light, a telltale sign of their youth, filled with hot, massive stars that burn furiously bright and fast. They are the direct offspring of the cosmic fire, forged in the single most energetic event a galaxy can experience. But that is only one way a galaxy acquires these stellar treasures. Another path is through cosmic cannibalism. When a large galaxy, like our own Milky Way, merges with a smaller dwarf galaxy, it does not just consume the dwarf stars and gas. It also devours the dwarf's entire system of globular clusters, absorbing them into its own vast halo. This means the population of globular clusters orbiting a galaxy is not a uniform family. It is a mixed collection, a cosmic archive assembled from many different sources. Some clusters are ancient natives, formed with the galaxy itself. Others are vibrant newcomers, born from a violent merger. And still others are immigrants, captured from smaller galaxies that were long ago torn apart and consumed. By studying the ages, compositions, and motions of these clusters, astronomers can perform a kind of galactic archaeology. They can read this stellar record to piece together a galaxy's history, identifying past merger events and understanding how the galaxy grew over billions of years. The silent, ancient globular clusters spinning in the halo of a galaxy are not just beautiful ornaments. They are the living testimony of its most dramatic encounters, the enduring witnesses to cosmic dances that shaped its very identity. But another invisible force is at work within the chaos, a ghostly presence woven through the very fabric of the galactic fog. Galactic magnetic fields, vast and unseen, are the cosmic architects of order within the turmoil. These fields are not abstract lines on a map. They are real physical structures, frozen into the ionized gas that drifts between the stars. Picture the interstellar medium as a vast magnetized fluid. When two galaxies collide, this fluid is not just compressed, it is violently stirred, twisted, and stretched. The magnetic fields trapped within it are dragged along for the ride, forced to follow every contortion of the gas. This turbulent motion does not dilute the fields, it supercharges them. The lines of magnetic force are stretched tight, like rubber bands being pulled to their limit, amplifying their strength and tangling them into a chaotic web. This newly intensified magnetic force then pushes back, influencing the very clouds it is tangled within. It can provide extra pressure, propping up a cloud against its own gravity and slowing its collapse into new stars. Or, in other regions, it can channel and focus the collapsing gas, guiding the flow of material and shaping the birth of stellar nurseries. This magnetic turbulence also acts as a colossal particle accelerator. Charged particles like protons and electrons can become trapped by these twisted field lines, whipping back and forth at nearly the speed of light. These are cosmic rays, and a galactic merger is one of the most powerful engines for their creation in the universe. We cannot see these magnetic fields directly, but we can read their signatures in the light they leave behind. Electrons spiraling at incredible velocities around these magnetic field lines emit a special kind of radio wave. This light is polarized, meaning its waves vibrate in a preferred direction that aligns with the invisible magnetic field. By mapping this polarized radio glow from a colliding galaxy, astronomers can trace the ghostly architecture of these amplified fields, revealing their intricate, tangled patterns. This reveals that the cosmic dance is not a solo performance guided by gravity alone. It is a breathtaking duet, a complex interplay between the pull of mass and the push and pull of invisible magnetic forces, both sculpting the future of the newborn galaxy. To witness a galactic merger from start to finish, you would need a time machine capable of spanning billions of years. Since we lack such a device, astronomers have built the next best thing inside supercomputers. These are not simple animations, but incredibly sophisticated virtual universes governed by the precise laws of physics. They are known as n-body and hydrodynamical simulations, and they are our primary window into the entire cosmic dance. An n-body simulation tracks the gravitational pull between countless individual points, each one representing not a single star, but a massive collection of them. This code calculates the subtle tugs and pushes that every particle feels from every other particle, a monumental calculation that reveals how stars are flung into tidal tails or sent on wild new orbits. But stars are only part of the story. The hydrodynamical component adds the all-important gas. It models this interstellar material as a fluid, simulating how it flows, collides, and shocks. The code includes rules for what happens when these virtual gas clouds are compressed beyond a critical point, triggering the birth of new star particles in a brilliant, simulated starburst. It even accounts for feedback, the powerful winds and radiation from those new stars that can push back on the surrounding gas, limiting further star formation. The process begins with a set of initial conditions. Scientists define the starting properties of two virtual galaxies, their masses, their speeds, and the all-important angle at which they approach one another. With these parameters set, they press a button and let the simulation run. Over days of computation, the supercomputer calculates the consequences, fast-forwarding through hundreds of millions of years of cosmic evolution in a matter of hours. The final output is a breathtaking movie of a galactic collision, a detailed prediction of how such an event should unfold. The true test comes when scientists compare these virtual creations to real-world snapshots, like the Antennae galaxies caught in mid-merger or the elegant, early-stage encounter of the mice. When the simulation produces the same long tidal tails, the same distorted shapes, and the same bursts of star formation that we see through our telescopes, we know the physics in our models is correct. These digital laboratories have been absolutely crucial. They confirm that the smooth, round shapes of elliptical galaxies are the direct result of major mergers. They showed how the complex dance of dark matter halos orchestrates the entire event from behind the scenes. They allow us to rewind and replay the history of our own local group, testing different scenarios for its past and future. Every time a simulation's prediction matches a new astronomical observation, it reinforces our understanding that the same fundamental rules of gravity and motion that govern a falling apple also choreograph the grandest ballet in the universe. Our galaxy's future with Andromeda is just one possible dance in a vast cosmic repertoire. The slow, complete merger is a dramatic finale, but it is far from the only interaction shaping galactic lives. Across the universe, a whole spectrum of encounters unfolds, each leaving a unique signature. Perhaps the most common event is the minor merger, a quiet form of cosmic cannibalism. A giant spiral like our Milky Way does not grow in isolation. It steadily feasts. Countless dwarf galaxies, small collections of a few billion stars, orbit these giants. Over time, their orbits decay, and the larger galaxies' immense gravity pulls them in, tearing them apart and seamlessly absorbing their stars and gas. This is not a violent collision, but a slow, steady accretion that builds up the galaxy's outer halo, one small bite at a time. Our own galaxy is currently in the process of digesting several such dwarfs, their stellar streams smeared across the halo like cosmic evidence of a recent meal. Then there is the galactic flyby, an event astronomers sometimes call galactic harassment. This is a near miss, a gravitational sideswipe where two galaxies pass close enough to feel each other's immense pull, but with too much speed and momentum to ever become bound. They do not merge, but they are never the same. The gravitational tides during this fleeting passage can still warp spiral arms, trigger modest bursts of star formation, and fling stars out into the void. It is a brief but impactful encounter, a gravitational handshake that leaves both galaxies permanently scarred and distorted. The ultimate fate of any meeting depends on a precise cosmic recipe. The relative masses of the two galaxies set the scale of the disturbance. The speed of their approach determines whether they have the energy to escape one another or are doomed to fall together. And the all-important impact parameter, the precise angle and distance of their closest pass, dictates the geometry of the resulting chaos. A direct head-on crash creates a very different kind of wreckage than a slow, grazing pass. This incredible variety means that no two galaxies share the exact same history. The majestic shape of a galaxy, whether it is a pristine spiral, a bloated elliptical, or a distorted irregular, is a living record. It is a cumulative archive of every encounter, every merger, and every close shave it has experienced over billions of years. We are not just looking at a snapshot of a galaxy, we are reading its biography, written in the language of stars. Even the ghostly halos of dark matter are not completely unchanged by this cosmic turmoil. While these vast spheres of invisible matter mostly pass through one another, their gravitational conversation leaves a subtle mark. The countless particles within one halo feel the collective pull of the other, a persistent drag that acts like a kind of friction in the void. This dynamical friction, as it is known, slowly bleeds energy from the system, helping to break the galaxy's orbits and draw them closer for their final merger. The chaotic rearrangement of billions of stars and immense gas clouds during the collision also reshapes the very gravitational landscape the dark matter inhabits. This violent relaxation forces the dark matter to settle into a new, altered configuration, changing the density profile of the resulting single halo. Some sophisticated computer models even indicate that the very center of the new galaxy could become less densely packed with dark matter than before, a counterintuitive result of such a massive collision. This is why observing galactic mergers is so crucial for science. They act as the only laboratories we have for studying how dark matter behaves under extreme gravitational stress. By comparing what our telescopes see in colliding galaxies with the predictions of these complex simulations, we can perform a fundamental test. Does the dark matter behave exactly as our models predict, or does its response reveal new, unexpected properties? The way this mysterious substance is stirred and redistributed during a merger gives us our best clues to the underlying physics that has governed the growth of every galaxy, cluster, and vast cosmic web we see in the universe today. Long before the majestic spirals and ellipticals we see today, the universe was a different place entirely. In its infancy, the cosmos was filled with a thick, neutral fog of hydrogen gas, a state that blocked light from traveling any significant distance. This era, known as the Cosmic Dark Ages, was broken by the ignition of the very first stars and galaxies. These pioneers were not the colossal structures of the modern universe, but rather small, fragile building blocks, mere proto-galaxies. And for them, the cosmic dance was not a rare event, but a constant, violent, and essential way of life. In that dense, young cosmos, these small galaxies were packed close together, and gravitational encounters were frequent and inescapable. They constantly bumped, merged, and cannibalized one another in a frantic scramble for mass. This relentless merging was the primary engine of growth in the early universe, the only way for these small fragments to assemble themselves into the first substantial galaxies. But these collisions did more than just build structure. They also transformed the very nature of the cosmos itself. Within these early, merging galaxies, the first generations of stars were not like our Sun. They were behemoths burning hot and fast, and their intense ultraviolet radiation began to eat away at the surrounding hydrogen fog. This process, known as reionization, was supercharged by the mergers. When two of these early galaxies collided, they triggered furious starbursts, just as they do today, but on a scale the universe would never see again. These bursts flooded their surroundings with a torrent of UV photons, and often, the mergers also fed the nascent supermassive black holes at their cores, igniting them as brilliant quasars. The combined fury of these merger-induced starbursts and active galactic nuclei acted like cosmic blowtorches, blasting vast, growing bubbles of transparent, ionized space into the neutral fog. This was the reionization epoch, a pivotal transition that lasted for hundreds of millions of years. It was a battle between light and shadow, where the chaotic, colliding galaxies served as the universal cleansing agents. Their violent dance systematically broke apart the primordial hydrogen atoms, stripping away their electrons and clearing the cosmic haze. Once the fog was lifted, the universe became the transparent realm we know, a place where light could finally travel across billions of light years without obstruction. Every photon from a distant quasar, every image of a faraway galaxy, journeys to our telescopes today only because of that foundational era when the first colliding galaxies choreographed the universe's grand awakening. The brilliant fire of creation cannot burn forever. After the starbursts fade and the central black holes merge, a profound quiet descends upon the newly forged galaxy. It enters a long, slow autumn, a period of cosmic aging where its most dramatic transformations are behind it. This future is dictated by a simple, stark reality: the exhaustion of its primary fuel. The violent merger consumed or expelled nearly all the cold, dense gas, the raw material required to birth new stars. Without this galactic lifeblood, the frantic pace of star formation grinds to a halt. Astronomers call such a galaxy quenched, its stellar population effectively frozen in time. The most massive, brilliant blue stars, those that lived fast and died young, have long since exploded as supernova. What remains is the slower burning, longer-lived population of smaller, cooler stars. Their collective light shifts from the fierce blue-white of youth to a warmer, mellower red glow. The galaxy becomes a smooth, red and dead elliptical, a celestial retirement community where stars simply grow older together. Its growth does not stop entirely, of course. It may still snack on passing dwarf galaxies or accrete wisps of intergalactic gas through minor mergers, but these are small additions, like adding a few new bricks to a completed cathedral. They do not change its fundamental identity or restart the grand engine of starbirth. This stable, passive state is the ultimate fate for many galaxies that experience a major merger. It is the final, lasting equilibrium, a testament to a powerful cosmic truth. The same violent event that brought brilliant life and dramatic change also sows the seeds for a long, quiet future. In the grand balance of the universe, the most intense destruction paves the way for a new and enduring form of existence. This grand cosmic recycling prompts a profound question about its ultimate yield. We know these violent mergers forge the heavy elements for planets, but can we actually find those new worlds? The search for exoplanets has so far been a local one, confined to the starry bounds of our own Milky Way. Yet, if the process is universal, then the merged galaxies we see across the universe should be teeming with planets of their own. Detecting a single exoplanet in another galaxy is a monumental challenge, pushing our technology to its absolute limits. The distances are so immense that the light from an individual star is a barely perceptible flicker. However, one method offers a glimmer of possibility, a technique that uses the universe itself as a magnifying glass. This is gravitational microlensing. Imagine a distant star in the Andromeda galaxy. If a massive object, like another star or even a planet, passes directly between that star and our telescope, its gravity will act as a tiny lens. For a brief moment, it bends and focuses the star's light, causing a temporary brightening, a flash in the darkness. The specific signature of that flash can reveal the presence of an orbiting planet. While we have not yet confirmed a planet in another galaxy using this method, the principle is sound. As our observatories grow more powerful and our surveys more persistent, the first extragalactic exoplanet discovery moves from a distant dream to an inevitable milestone. Finding a world orbiting a star within the chaotic swirl of a merged galaxy would be the ultimate validation. It would prove that the cosmic dance is not just a creator of stars, but a prolific architect of entire planetary systems. Such a discovery would tell us that the ingredients for new worlds are sown everywhere, even in the most turbulent and energetic nurseries the universe has to offer. These cosmic events paint some of the most breathtaking masterpieces in the universe. The Hubble Space Telescope has gifted us with a gallery of these interactions, where science and art become one and the same. We see the delicate, sweeping curves of tidal tails, glowing with the light of billions of exiled stars. We witness the fierce, blue-white fire of starburst clusters, blazing like diamonds scattered across velvet. Intricate lanes of cosmic dust weave through the scene, their dark filaments tracing the ghostly contours of magnetic fields and shock waves. This is not random splatter, it is a direct and vivid portrait of the universe's deepest laws. Every graceful arc is a line drawn by gravity's invisible hand. Every brilliant knot of newborn stars is a signature from the laws of hydrodynamics, where colliding gas clouds ignite under immense pressure. To stand in awe of the Antennae galaxies is to feel the force of gravity and witness the birth of stars, all through the medium of pure, visceral beauty. This aesthetic dimension does more than please the eye. It bridges two ways of understanding our place in the cosmos. It connects the analytical rigor of science with the innate human capacity for wonder. In these celestial collisions, we see that the universe is not just a machine to be decoded, but a source of profound and moving artistry, reminding us that the forces which shape existence are capable of both brutal power and exquisite grace. Our galaxy's inevitable collision with Andromeda shatters any illusion of a static cosmos. This cosmic forecast forces a profound shift in perspective, moving us from seeing the universe as a permanent backdrop to understanding it as a stage of relentless, dynamic transformation. The grandest structures we can conceive, entire galaxies of hundreds of billions of stars, are not eternal monuments. They have birthdays, they live long and eventful lives, and they ultimately transform into entirely new entities over timescales that dwarf human history. This reality is both humbling and strangely empowering. It places us squarely within a living, breathing universe, one that is actively being built and rebuilt in an endless cycle. We are not just passive observers looking out at a frozen celestial museum. We are living on a planet orbiting a star within a galaxy that is itself a participant in this magnificent, slow-motion ballet. Every element that makes up our world, from the iron in the core of our planet to the calcium in our bones, was forged in the heart of a long-dead star. That star itself was likely born from the enriched debris of a galactic collision that occurred billions of years before our Sun even ignited. This means the very processes that seem so violent and destructive on a cosmic scale are the same ones that meticulously crafted the building blocks of our existence. Understanding this grand narrative weaves us into the fabric of the cosmos. It suggests that our origins are not a local, isolated event, but part of a continuous, universe-wide rhythm of creation, destruction, and renewal. We are not just in the universe is in us, and its most dramatic dances are part of our own deep history. This cosmic dance reveals a universe that is anything but still, a vibrant arena of constant transformation. We have journeyed through the slow-motion collisions where gravity's pull orchestrates not destruction but breathtaking creation. These encounters ignite stellar firestorms, forge the elements for new worlds, and sculpt the majestic elliptical galaxies that dot the heavens. Our own galactic home is destined for such a merger, a future written in the silent, relentless motion of Andromeda. Even the ancient globular clusters orbiting our Milky Way stand as enduring witnesses to long-completed encounters. This grand process is not a rare catastrophe, but a fundamental thread woven through the entire history of cosmic evolution. It is a powerful reminder that from profound chaos can emerge a new and enduring order, and from the ashes of old stars can spring the very ingredients for new life. So the next time you gaze at the night sky, see it for what it truly is, a single, fleeting moment in a billion-year-long performance. You are watching a celestial ballet that continues to spin new suns and new possibilities across the unimaginable vastness of space. This grand story of galactic collisions is still being written, with astronomers making new discoveries around every cosmic corner. If this journey through the cosmic dance has ignited a spark of curiosity within you, the exploration has only just begun. You can witness this breathtaking beauty for yourself. I urge you to seek out the raw, unfiltered images captured by the Hubble and James Webb Space Telescopes. Look for the Antennae galaxies, a tangled knot of blue star clusters and crimson dust, or the elegant, long tails of the mice. Seeing these real celestial portraits makes the entire phenomenon feel vividly, undeniably real. We would love to hear what resonates with you most in the comments below. What part of this cosmic drama captures your imagination? Is it the silent fate of solar systems, the forging of new elements, or the future of our own Milky Way? Your thoughts and questions fuel this shared exploration. If you are eager to continue unraveling the mysteries of the universe together, please subscribe to the channel and tap the notification bell. That way, our next adventure into the cosmos will be waiting for you. Thank you for joining me on this journey. Keep your eyes on the skies and never stop wondering.